Hello and welcome to the last of these chats about resistor networks, in which we'll be looking at some hard ones. Okay, first, what do we do here? It's a resistor network. It's a network purely made up of resistors. It does have an equivalent resistance, so that the voltage from A to B is proportional to the current flowing into A and flowing out of B. But how do you analyze that? There are no two resistors in parallel, and there are no two resistors in series. So how do you even get started? Well, fortunately, there's a trick to this one. Quite fond of little tricks. This little trick is an exception. Most of these circuits are really hard to solve, but this one isn't. Because, have a think about this. Supposing that 1K resistor in the middle wasn't there. We'd have a circuit which looked like this. A would go up through a 6K resistor and go into a 3K resistor and then down to B. And this would come through a 4K resistor and a 2K resistor and then go to B. And we won't put in the 1K resistor for now. Right. What voltage is this node here at? Well, this is the potential divider. The same current must be flowing through this resistor as is flowing through this resistor. But this resistor is twice as big as this resistor. Therefore, the voltage across this 6K must be twice as big as the voltage across this 3K. We know that for any resistor, the voltage across it is the current flowing through it times the value of the resistor. They have the same current flowing through them. This resistor is twice this one, so the voltage across this one must be twice the voltage across that one as well. And the same is true down here. 4K is twice 2K, so the voltage across the 4K resistor must be twice the voltage across the 2K resistor. This is 2 times that. But this plus this must be the voltage between A and B, and the same is true of these two voltages. This voltage and this voltage difference must be the voltage difference between A and B. So, this voltage here must be 2/3 of the way from A to B. If A was 3 volts and B was at ground, then this point here must be at 1 volt. So that 2/3 of the voltage, in this case 2 volts, drops across the 4K resistor and 1 volt drops across the 2K resistor. And the same would be true up here. This point is 2/3 of the way in voltage between A and B. In this particular example, where this is 3 and this is 0, this would be 1 volt as well. So we now come along with our 1K resistor and we add it into the circuit. We just drop it in. But both sides of this 1K resistor are at the same voltage, which means that there's no current flowing through the 1K resistor. If there's no current flowing through the 1K resistor, it's not doing anything. We don't have to consider it. The circuit wouldn't change its behavior at all because we've added the 1K resistor. So we can ignore it. We can just analyze this as a 6K and a 3K, which would be a 9K resistor, in parallel with a 4K and a 2K, which would be a 6K resistor. And using the standard techniques that we've got before, the equivalent resistance of that would be 9K times 6K over 9K plus 6K, which is just 9,000 times 6,000 divided by 15,000. The answer 3K6, 3,600 ohms. Right. What about if these two resistors were not in the same ratios, though? Now we've got a problem. Now we've got a big problem. Because now, if I take the 3K resistor out of this circuit, the voltage here is not the same as the voltage here. So there will be some current flowing through that 3K resistor. But I haven't got two resistors in series or two resistors in parallel. How do I even start analysing this circuit? Well, the techniques that we've talked about so far don't work. I have to introduce you to a new technique, a rather more advanced one, something called the delta Y transformation. And it goes like this. A 3-terminal resistor network, which looks like this, a so-called delta shape. It's actually a delta upside down, but for some reason it's called a delta shape, is equivalent to a 3-terminal network that looks like this, known as the Y network. And if you choose the resistors correctly, you can swap out one of these networks, a 3-terminal network, with another 3-terminal network, and the rest of the circuit would behave exactly the same. The equations that you need, and I won't go through the derivation of them here, that's beyond the syllabus of this module, do have a look up if you're interested. The important thing is to recognise that this transformation exists and we can use it. And you can go from a delta network like this to a Y network like this using these transformation equations. So, let's have a look at these values and see what we can do here. We'll take these 3 resistors here, and if I draw this in a slightly different way, the same topology, I'm just going to draw it like this. 6K, 9K, 3K, and then there's a 2K resistor here, and a 1K5 resistor here, and they go off to node B. Right, that is a 3-terminal delta network, which we could transform into a 3-terminal Y network using these transformation equations. So we can transform it into this. A single resistor goes into a central node there. There's then a resistor coming out of that central node, which would be to this point here. And another resistor coming out of the central node, which would be this point here. I'll call that C and D. That's C, that's D. Then C carries on through a 2K resistor, D carries on through a 1K5 resistor, and they both join up to point B. And we can work out what these 3 resistors actually are by plugging the numbers into these formulas. Let's have a go. First one up there, R1. That's going to be this resistor here. R1 is the product of the 2 resistors which are connected to point X divided by the sum of the 3 resistors. So in our case here, that would be 6K times 9K divided by the sum of these, which is 18K. So 6,000, I'll just work in terms of 1,000 ohms, it will be quicker. 6 times 9 divided by 18. The answer is 3K. This resistor here, R1, is a 3K resistor. The resistor R2 here, which is this one here, that is the product of the 2 resistors which are connected to point Y, RA times RC, divided by the sum of the 3 resistors. Well, in that case, that's going to be 6 times 3 divided by 18. That's 1. This is a 1K resistor. And this resistor here, connecting to point D, that's the product of the two resistors that connect to point D divided by the sum of all of the resistors. So that's going to be 3 times 9 divided by 18. That's a 1K5 resistor. Right, that looks better. These two resistors are in series. So we can replace them with a single resistor, which has the sum of these two resistances, 3K. These two resistors are also in series, so we can replace them with a single resistor, 3K. They join up at that point there, and they join up there and go to B, and there's a 3K resistor here going to A. Okay, these two resistors are in parallel, and they're equal. So we can replace them with a single resistor, which is half the value of one of these two resistors. 1K5, like so. And then I've got two resistors in series, which I can replace with a single resistor, which has the sum of those two resistances. 3 plus 1.5, 4K5. So that rather unpleasant network down there actually behaves the same as a 4K5 resistor. We can check it out in the simulator, just check that I've got my maths right. Okay, remember we predicted this was going to be a 4K5 resistor in total. This resistance here behaved like a 4K5 resistor. See, the total voltage across it, in this case, is 1 volt. The current flowing through it, 222.2 microamps. So the resistance, the equivalent resistance, must be 1 divided by 222.2 microamps, which is as near as it can get, given the fact that I haven't put in all of the decimal points, of 2, yep, 4.5 times 10 to the power of 3, or 4K5. Works. As I say, the derivation of the formula for the delta Y transformation is outside the syllabus, but it's important to know that it does exist, because on some of the level 4 quiz app topics, if anyone is keen to have a go at those, you will need the delta Y transformation to be able to solve them. Okay, that's all I wanted to say about resistor networks. See you at the next one.